Hello everyone, today I'm going to be talking about the transformer and the self-attention layers. Now the transformer is used by large language models, and you probably already know one large language model, and that is the GPT models, which ChatGPT uses. So today I'm going to be going through the architecture from the attention is all you need paper, because all other transformer architectures are descendants of this one. So therefore, if you're able to understand the architecture of this transformer, you'll very easily be able to understand newer transformer architectures. So without further ado, let's just dive right in. The transformer that you see here consists of an encoder on the left side and a decoder on the right side. Here to begin with, I would like to show you how input is being processed and essentially how the transformer accomplishes a task. Let's say the task is to translate this sentence, "Hi, my name is," from English to Danish. First, we need to represent the words in the sentence by their word embedding vectors. And a word embedding vector is just a way of representing a word by a corresponding vector. These are stored in a matrix as you see here, and this would be the input to the encoder. So in the input embedding step, that is where the words are put into this matrix, where each row corresponds to the word embedding vector of that word. Next is the positional encoding. I'm not going to go into detail with this one, just understand that the word embedding vectors are slightly changed based on their position in the sentence. Then what happens is the input is sent into the encoder. And the first step here is this attention layer. And it is the attention layer's responsibility to contextualize the input, so find connections between the words and so on. And then it is sent into the feed-forward neural network. And there you have it. Now the encoder has some representation of the input, which is then ready to be used in the decoder. Alright, so how does the decoder work? Well, it's the decoder's responsibility to predict the translated sentence. And the way it does that is through an iterative process. So the first input to the decoder is this beginning of sentence token. And that goes in, then it goes into the attention layer, and then the next attention layer, and in this attention layer you also use the output from the encoder to help with predicting the next token. Then it goes through the linear layer and a softmax layer that just gives probabilities to every single word in the vocabulary, and then it randomly picks the next word based on probabilities, and that should hopefully be the correct translated word. Then it goes through this process again, now with the input beginning of sentence and the next and the correctly predicted word. Go through it, predicts the next word, which is hopefully this word. Then it uses this as input to predict the next word, and finally it goes through the whole process again to predict the final word, and there you have it, a translated sentence. Alright, so to understand the math in the transformer architecture, you would have to understand the positional encoding, the attention layers, the add and normalization layer, and the feed-forward neural networks, and how the math works in the softmax. Now I'm going to focus mainly on the math in the attention layers, because that is what I found most difficult to understand, so that's what I want to focus on. Okay, so I can quickly go through the math of the layer normalization in a short way. So it is simply this X is represents this arrow here. So it is basically the input before it enters the attention layer added with the output of the attention layer, and that's it. And then here it's the same, but just before it enters the feed forward layer. Okay, now let me focus on the math of the attention layers, and it is slightly different based on if it's the masked multi-head attention or just the multi-head attention layers. Now, I'm going to ignore the multi-head for now, and I'll explain that later. Now I'll just show you how you actually calculate attention. And the way it's calculated is like this. It is represented by three matrices: queries, keys, and values. And these queries are calculated or represented by vectors. And these vectors are calculated by multiplying the word embedding with the corresponding weight matrix. And there is a weight matrix for each of these three matrices: WQ, WK, and WV. And it is these weight matrices that you tune when you train the model. So you multiply them together, and then you have a representation of these matrices, and then you can just use it in this formula. And that's it. Now, the dimension of the weight matrices are like this. D model is the word embedding dimension. So it is how many values each vector that represents the tokens use. DQ is just some chosen value of how large you want the matrix to be. And these are usually the same because that makes it easy to do matrix multiplication. Alright, it is worth mentioning what happens in this layer. This is actually the cross attention layer because there's some output from the encoder that goes into the decoder. And what these two arrows represent is the key and the value. So you use the encoder's output to calculate the key and the value matrix, and you use the output from this decoder step to calculate the query matrix. So that's just what happens here. Okay, now let me focus on this part here, which is preserving the autoregressive property. And this happens in the masked multi-head attention layer. And this is because the decoder is only allowed to read the input sentence from left to right, and not from right to left. So just like we would read a sentence. So therefore, you remove any influence from future tokens. For example, this is the key for the token my, and this is the query for the token high, and therefore you put it to negative infinity. Then when it is run through the softmax, this negative infinity becomes 0. This is however not the case in these two layers, where it is allowed to utilize bidirectional context understanding, so left to right and right to left. So there, these values would just be some other value. And what this does is that it allows the encoder to read the input sentence that you want translated, or the input sentence of some other task you want to solve, and you let it use bidirectional context understanding to get a good understanding of the input sentence. Then to generate new tokens, you have to preserve the autoregressive property, this left to right property, and that's what happens in this layer. This allows us to predict new tokens iteratively. Okay, now we just have to understand multi-head attention. Up until this point, we've used only one weight matrix for each Q, K, and V. And you can think of that as the brain of each of these matrices. Now instead imagine that we use a bunch of smaller brains that each focus on some certain aspect of the sentence. And why use a bunch of smaller brains? Well, it's just been proved that it generalizes better. So that's why you do it. And what you do is that you calculate attention with these smaller brains as you would using this formula, and then you concatenate it in the end. The dimension of these smaller brains uses the same pattern as before. You just have more of them. So here, for example, when you set DK, DQ, and DV equal to each other, you have the dimension of your word embedding and the number of heads that you want, and that equals 64 if the dimension is 512 and the number of heads is 8. And then you just have 8 of these matrices, 8 of these matrices, and 8 of these matrices, and just one of these matrices, because when you multiply H with dV, that will equal 512 again, so we have a 512 by 512 matrix. And when you concatenate these heads, which is the same as just placing the matrices next to each other from left to right, which means that you'll just have a D model 512 rows by 512 columns. And that's it. And then you can calculate these heads in parallel, so the compute time doesn't become much longer. And that's really it. If you're able to understand this, then you now have a great understanding of the transformer architecture, which can help with your understanding of large language models and how they might work. So, I hope you now have a great understanding of the transformer architecture, consisting of both an encoder and a decoder, at least the parts that I found very difficult to understand when I first learned about the transformer. I hope you enjoyed this video. Feel free to drop a like or comment if you have any questions, and I'll hopefully see you again in my next video. This is not the last time I'll be talking about transformers.